Electron configurations for atoms. Last time we were introduced to Dr. Niels Bohr, and he has this interesting quote. He says that if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Now, in more advanced chemistry classes, you'll get, I think, a better feeling for what he's talking about, but I think you're already getting an inkling. I mean, this is some really weird stuff, and these rules just seem to be coming out of nowhere, but it works. Quantum chemistry works. We saw how last time different elements emitted different colors, and the only way to explain that, the only way to describe how that happens is to say that these electrons for these different elements can only take on certain energies, and those energies are different for the different elements. So to date, quantum theory explains the chemistry of the very small better than anything else that we have. So today we're going to talk about the arrangement of the electrons. We're going to call it electron configuration. And it's this electron configuration, it's this arrangement of the electrons that determine all the properties of an atom. Now, not this type of property though. This is a nuclear explosion. This is nuclear chemistry. Actually, the nucleus is undergoing a reaction. So we're not talking about nuclear chemistry. We're talking about every other type of interaction that an atom or an element exhibits. And we are going to see it's really the outermost electrons, the most energetic electrons of the atom that really determine the chemical properties that we're talking about. And again, not nuclear chemistry. This is regular chemistry here. So how do we know how to write the electron arrangement or the electron configuration of an atom? It's all dependent on the energies of these atomic orbitals. You just fill the lowest energy first. That's all you got to do. So an electron configuration consists of placing all the electrons an atom has in atomic orbitals from the lowest energy to the highest energy. And the number of electrons that fit in any orbital is 2. So we can see here's increasing energy going up, and so that means this is the lowest energy, lowest atomic orbital. Here's our highest atomic orbital, higher anyway. And notice how there's only one line, so there's one orbital, 3 orbitals. Do you remember that? Because since it's an s orbital, it's s, that means L is 0, so m sub L can only be 0. There's only one value, so there's only one orbital. Look at the p. With p, L is 1, so m sub L, -1, 0, 1. So there's 3 orbitals, and that's why there's 3 lines. With the d, there's 5. There's 5 orbitals, okay? So how do we know the order in which to fill these atomic orbitals? We know it's the lowest to the highest energy. I see 2 options. The first option, yuck. Memorize the Aufbau diagram above. Know that. I mean, you have to remember 1s is first, and there's only one orbital. 2s has one orbital, and then it's 2p, and it's 3 orbitals. That's too much to know. I think option 2 is the way to go. Know which atomic orbitals are being filled in the different sections of the periodic table. The entire periodic table is designed because of the electron configurations of the elements. So let's know which sections are being filled with which atomic orbitals. So in the periodic table, hydrogen has 1 electron, helium 2, lithium 3, beryllium 4, boron 5. So see how the order is being filled here with electrons. So what's being filled first? 1s. So this is still 1s, right? Because 2 electrons can fit in an orbital. So we're filling the 1s. Now the next energy is 2s. And then we're filling 2p. 3s. 3p. Notice that we are following Aufbau's principle. 1s, and then 2s, and then 2p, 3s, 3p, 4s. Same thing. It's a lot easier though. We have 4s. In fact, this is all s. 5s, 6s, 7s. These are all p's. 2p, 3p, 4p, 5p, 6p, 7p. Now the d's. 3d, 4d, 5d, 6d. And then these lanthanide and actinide series, 4f and 5f. So know this. Which sections of the periodic table are filling which atomic orbitals? And if you are familiar with that, we just need to know a couple rules, and we're going to be able to write electron configurations for atoms. Let's take a look at those two rules. The first rule is the Pauli exclusion principle, and the second rule is Hund's rule. So let's see how this works. So let's try writing the ground state electron configuration for a nitrogen atom. And ground state just means lowest energy. So don't really worry about that. That just means don't skip any orbitals when we're writing the electron configuration. So what we're going to do is we're going to fill in electrons until we get to 7, because 7 is the number of electrons in a nitrogen atom. So where do we start? Well, we start with number 1. What are we filling first? 1s. And then what do you fill next? You fill 2s. Then what do you fill? 2p. But we don't need to keep going because nitrogen is within the 2p. Now let's just add the electrons. 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3. There we go. That is the electron configuration for a nitrogen atom. 1s2, 2s2, 2p3. Now when it asks for an orbital diagram, a little bit different. It wants us to draw a picture. It wants us to draw lines or boxes and arrows for the electrons. So no big deal. We'll have 1s, 2s, 2p. Now how many boxes do you draw or lines do you draw for an s? There's only one orbital. Just draw one orbital. 2s, just draw one orbital. But in p's, there's 3 orbitals. So now we fill it up. If the first electron's going up, the second one has to go down. That's Pauli's exclusion principle. So if you draw the first one going up, the second one has to go down. Now we have 3 electrons left, right? 2p needs 3 electrons. So where do you put them? Well, first one up, second one down. Okay. Applying Hund's rule means you want to write these electrons in the lowest energy configuration. So according to Hund's rule, this is wrong. What we need to do is spread them out and all in the same direction. So all up or all down. And all in a different orbital. That's Hund's rule. That's the lowest energy possible. That's the ground state. So when I ask for an orbital diagram, it looks like this. Write the ground state electron configuration of arsenic. Okay, so we're going to fill in all these orbitals until we hit arsenic. So keep going, keep going, keep going until we stop here. All right, let's try it. So we'll have 1s2 and here, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, 4p2, 4p3. There we go. noble gas core notation. Noble gas core notation is a shorthand way to write electron configurations for atoms. And it's nice. Let me show you what I mean. Write the ground state electron configuration of arsenic using noble gas core notation. So this is what it looks like without noble gas core notation. With noble gas core notation, all we do is we find what we're looking for in the periodic table, arsenic, and go back until we hit a noble gas. We hit argon. So what we're going to do is we're going to start at argon and then do what we did before. So noble gas core notation, find the nearest noble gas. In this case, it's argon, and then keep going. So after argon is 19, so we have 1, 2, 3, 4s2, 3d10, 4p1, 4p2, 4p3. So you see what we got to do? We just got to skip all of this and just wrote argon instead. Valence electron configurations. The valence electron configuration of an atom consists of the electron configuration outside of the noble gas core electron configuration, or pseudo noble gas core electron configuration. What are they talking about? Okay, the idea of valence electrons is that the outermost electrons, the most energetic electrons, are doing all of the reacting. They essentially control the properties, the chemical properties of this element. So how do you figure out what those valence electrons are and write only their configuration? What you do is identify the noble gas core or pseudo-noble gas core and just don't write that part. For example, we said that this is arsenic's electron configuration. So don't include the noble gas core. Don't include that part. Don't include pseudo-noble gas core. That's D10. Anything D10. Don't include that. So what's left? 4s2, 4p3. That's the answer. 4s2, 4p3. Now it seems kind of complicated, but there's a real hint here. How many electrons are here? We have 2 from the 4s2, we have 3 from the 4p, we have 5 valence electrons. That matches what the periodic table says. Look at arsenic. The Roman numeral above it is 5. So everything here has 5 valence electrons. Everything here has 7. Everything here has 8. Everything here has 2, 1. So that's the idea here, is that the valence electron configuration has to match what the periodic table is giving you. But here's my answer. Which of the following orbital diagrams are not allowed due to the Pauli exclusion principle? So remember the Pauli exclusion principle? Here's an example, one that's breaking the law there, right? Here again, we have 2 electrons with the exact same set of quantum numbers. So that won't work. Now this one is breaking Hund's rule, but they're not asking about that. Circle the following electron configurations that are possible. This is kind of a trick question. I'll show you why. Let's take a look at the first one. We can see that you can't have that. No, you can't. That's wrong. You can't have 7 electrons, so don't circle this one. Do we circle B? Notice that this is not filled. And that electron it got promoted way up there. That's all it did. It just jumped up to the next higher energy level. That's very possible. They call this an excited state. This is definitely not the ground state. So that is definitely not the lowest energy configuration. So that's why they call it an excited state. but it's possible, so we'll circle it. Is C possible? You bet. How about D? Everything looks good. What'd they do? They promoted an electron way up there. How did that electron get up there? Well, it absorbed some energy. It absorbed the exact energy difference between those orbitals, and it got up there. So this is very possible. It's just an excited state, not the ground state. Give the electron configuration of the ground state of iodine. Now do this with and without the noble gas core notation. Okay. Iodine. Way down here. So keep filling the atomic orbitals until you hit iodine. See if you get the same answer as me. So I'll start with the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p1, 5p2, 5p3, 5p4, 5p5, and that iodine. So using noble gas core notation, find the nearest noble gas. Go back, krypton. Do the same thing, just start at krypton. So I will start down here. It's 5s2. 4d10, 5p5. Zirconium is a group 4b element in period 5. So here's 4b, there's zirconium. What would you expect for the valence shell configuration of zirconium? So let's write its noble gas core notation and cross out the noble gas and any pseudo-noble gas core that we see. So for zirconium, the nearest noble gas is krypton. We have 5s2, 4d1, 4d2. Now remember, the idea of the valence shell electron is that everything outside of the noble gas and the pseudo-noble gas. We don't have any D10, so we're done. Our answer is 5s2, 4d2. Does that make sense? 4 electrons, group 4. What would you expect for the configuration of the outer electrons of manganese? Outer electrons just means valence. So where's manganese? Here it is. Let's go ahead and write our noble gas core notation. First noble gas is argon. Then we have 4s2, 3d1, 2, 3, 4, 5. To determine the valence electron configuration, remember, don't include noble gases. So there's our answer, 4s2, 3d5. When writing the lowest energy, i.e. ground state configuration, it is important to follow Hund's rule. And we know that. It is also important to realize half-filled D subshells, D5, and full D subshells, D10, are extremely stable. So write them when you can to predict the correct ground state. Write the noble gas core electron configuration of the below elements. Let me show you what I mean. Copper. What's the noble gas core electron configuration of copper? Well, we start with argon. And we're down here. 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d9. we are very close to D10. So they're saying that this is wrong. The right answer is 4s1, 3d10. Because then we only have one valence electron. That's why copper only has one valence electron. And it's in group 1. Vanadium. Vanadium is here, so its noble gas core notation is argon, 4s2, 3d1, 2, 3. 3d3. Okay, so what the book is trying to say is that this is wrong. Promote those 2 electrons to D5. That's the answer. So whenever you can make D5 and D10, do it. That's how you get the correct ground state electron configurations for those transition metals. So here's the big test. Give the electron configuration of the ground state of cobalt. Do with and without noble gas core notation. Okay, so here's cobalt. Let's do without first. So we'll fill 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, 3d2, 3d3, 4, 5, 6, 7. The noble gas core. Argon is the nearest noble gas. For S2, 3d7. Notice that we really can't promote any electrons because we only have 2 to promote. And we don't have any place to lose those 2 to make D5, so we can't go either way. So there's our answer. So I think the main idea here in writing these electron configurations, how are the electrons arranged energetically in every single atom? Know the atomic orbitals and how they're filled within the periodic table. And you shouldn't have much trouble. Good luck.